Okay, welcome to the next lecture, uh, post going fully online. This lecture is for Wednesday, March 18th. I want to remind you all that you do have a programming assignment. It was posted on Moodle. You do need to read the book in order to learn. Um, a colleague of mine who teaches in North Dakota posted recently that switching to online, which they are doing as well, um, he said, now the emphasis becomes even more intense upon the learner. That is, that learning has always required the participation, the active participation of the learner. But in these circumstances, even more emphasis and even more uh, sort of engagement is required by the learners, which is you. I can only do so much with these online courses, and we really do need to read the book, look through the PowerPoints, do the programming assignments. And if you don't do the work, you know what happens. So I'm going to share my PowerPoint. And we're going to talk a little bit more about data structures. And in particular, we'll talk about data structures that are what we call the linear data structures. We've already briefly discussed linked lists and stacks, but there are many basic data structures that anyone with a degree in computing should know. Those are the linear data structures, stacks, queues, and linked lists, but also nonlinear structures such as binary trees or heaps or B-trees. Now, binary trees, heaps, and B-trees, we aren't going to cover in this course. Those are all topics for CSI 201. But stacks, queues, and linked lists, we are going to spend all of our time on those data structures for the rest of the term, okay? Now, for any of these data structures, we know what they are, we know how they work, but that isn't tied to any particular language. If I talk to a computer scientist and I say, I need to implement a queue, they know exactly what that queue does. They really don't need to know what language it's in order to understand how the queue works. And so in that way, these data structures are what we call abstract. That is, they are abstracted away from the language, and they are can be implemented in virtually any programming language. Now, this leads to the idea of abstract data types, or ADTs. We want to design programs that have modularity. That is, that the complexity is kept manageable, and that we're able to develop a data structure like a stack independent of the other code that's going on in the application. Okay, so the stack is just a building block that's used by an application program that somebody's writing. Same thing with a queue, same thing with linked lists, same thing with any of those data structures. Those data structures are just simply like an array. We don't talk about arrays as being very specific. We talk about them as being this generic thing that we can store data in and that we can use in our programs. So stacks are the same way. Stacks are these generic data structures that we can use to store data in. Queues, same thing. Linked lists, same thing. Heaps, binary trees, B trees, all kinds of data structures are generic, and then we can use them to build more powerful and complex programs. So we have this idea of modularity. The data structure is modular. It's implemented separate from the actual data that's stored, separate from the application program that's using the data structure. So that helps keep the complexity manageable, and it also provides the ability for us to develop and test independently from each other so that multiple people can work on the same program. And this also enables code reuse. That is, I'm not going to implement a stack, every time I need a stack. I'm going to go back to that code, go back to that class that I developed or the struct that I developed, and I'm going to reuse that. And I'm going to reuse it, hopefully, without having to retest and re-implement. And the other part about these abstract data types is that we're separating the data type business from the application data business. And that means that we're doing information hiding. That is, we're going to only allow a downstream programmer or user the access that's required to our abstract data type, and only under the conditions that we deem proper, okay? At the same time, the application programmer or the downstream programmer, although they don't get the access to everything about our abstract data type, they also can hide their data from us. We're implementing the data structure. We don't care about what their data is. And we really shouldn't know what their data is. We need to be abstracted. So there's a classic textbook in data structures related to object-oriented programming. And that textbook speaks of this as walls and mirrors. That is, the walls keep things protected. So we're talking about information hiding as well. So let's go a little bit deeper into the information hiding. The user of our data structure should not need to access how our data structure is implemented or the nuts and bolts of it. For instance, in a stack, we're doing dynamic allocation that involves memory addresses. The end user of our data structure should not have access to those memory addresses, because around those memory addresses are other variables, other pieces of information. They could exploit that to get access to stuff that they shouldn't have access to. And so we want to keep those memory addresses, the areas of memory where we're storing and building the data structure, away from those end users. Now, those end users, though, are still programmers. They're just building an application program that uses our data structure. Now, the developer of the data structure, this end user of the data structure, our code shouldn't be able to have access to their application data. For instance, if I'm building a abstract data structure or an abstract data type that stores data on medical records, then there's a whole ton of regulations about access to that application data, to those medical records. HIPAA, the Health and Information Privacy Act, keeps us from being able to see that data. Same thing with FERPA. If this is student data and I'm just building a data structure, an abstract data type, I shouldn't be able to see any of that student data while I'm building or while I'm working with the abstract data type. And so there's no need for me to have direct access to that application data. And I should not know what that application data is. And we'll see this become more important when we get to linked lists and the things that we will do in order to keep that abstracted away. Now, basically, information hiding is security. We want security to keep certain data out of the public eye. We also want to potentially have levels of security so that a system administrator sees some data. The example I always use is a medical record system. In a medical record system, the doctor should be able to see your past tests and your conditions and your medications. The person in the billing office should not be able to see that. There's nothing about their job function that says that they should be able to see what your test results were. They might have to, and probably do have to, see that you had a test done because there's a certain cost with that test, but they shouldn't see the results. Think about it. What happens if the billing person at War Memorial can see the results of a cancer screening? Oh my goodness, that's horrible. And so you want to have those different levels of access depending upon the role of the person involved. And inside of the abstract data type for the application data that the end user is doing, they can control that access. And so this is all about security, and it's all about access. Who gets to access what is the way that you implement security. And you'll find this throughout your career. Security is access. The most secure computer from viruses in the world is a computer that is not connected to the internet and doesn't allow any external media to connect to it. Well, that's not very useful, right? But still, that's what security is. It's access. Information hiding allows us, the programmers, to control who gets access and how much they can access. And then we have two ideas that are called accessors and mutators. Sometimes you hear these called setters and getters. And these functions are included for verification and for data encryption. All kinds of code can go into these accessors and mutators. You can do range checking and error checking. And so those are another way of controlling who has access and what they can do. And so we'll look at an example in today's lecture on how to do that, how to set that up. Now, ADTs in C++ come as classes. This is an idea sort of expanding upon the idea of structs and unions that were in C. We've already got a program where we're building a stack with a struct. And in fact, even in a class, we'll build those data structures using structs, but all of the code that goes with it. Remember, we had those functions in the programming assignment. I gave you a couple of them in a demo. And then there's a couple more that you have to write. Those functions only work on that stack. But I could call the functions and give them a pointer to I don't know, another data structure, another type of data structure. And that function would do something unexpected, or maybe even fail and cause an error because we're not using the function in the way that it was designed. Classes take not just the data, the struct, but they also take the functions that work on it, and they put them all into one container. So a class, just like a struct is a container, a struct can only contain data. A class contains both code and data. And so that's what we're headed to. So the data members for organization, that is for building the data structure, functional members, sometimes called methods, to add data, to remove data, to query data, and query is a term comes from database. That means to ask a question, and to manipulate data, that is to change it. And so we're going to take a look at all of those kinds of things when we get to classes in just a few slides. Now, why classes? Well, we have a problem with structs and the functions that work on them because they require things that shouldn't be seen, like pointers, memory addresses, need to be available for the user of the data structure. So like star head was in main in the stack program. Well, the application programmer shouldn't know how that stack is implemented. They shouldn't have access to the memory addresses, but head gives them that access. And so that's a security problem, that's a danger. Often the type and the format of the application data must be accessible by the developer of the data structure. And so when we're doing this in structs, we had to know that there were characters, and that had to be included in the struct for the stack node. In classes, that's no longer the case. And so in classes, we can get around this so that the data structure that we're building doesn't know anything about the application data. Okay. Now, I'm going to do a little bit of an approach to how we do these classes. And this is a common sort of standard thing to do in programming classes, in developing classes. And that is, we use two separate files for a class. One is the definition, which we call the specification, and it defines what the class looks like. And the other is the implementation. And the implementation is the actual code for the functional members. So that convention in building classes is used everywhere, okay? And the specification is put into a .h file, which is usually the class name. So if we were building a stack, let's say, we would have stack.h. If we were just building like a sensor network node or a class for sensor network data, we would have sensor.h. And it contains all the prototypes for the functional members of the class and the definition of the data members for the class. The implementation is referred to by class name.cpp, so that would be like stack.cpp or sensor.cpp, and it contains the code for all the functional members. So no code goes in the .h, and this is something that drives people, longtime old school programmers, up the wall. Don't put code in the .h. When you put code in the .h, people will hunt you down, they will hurt you, they will treat you poorly. They will, it's just one of those things that, you know, you do not do that. You do that with me, you're going to get marked down. You do that with Shem, you're going to get marked down. We both have the same sort of old school attitude to programming where that's concerned. Okay, so two files for each class that you develop. A .h file called the specification, and a .cpp file that we refer to as the implementation. Now the specification, all classes need some certain functional members, and two required ones are a constructor and a destructor. There are a couple of other ones that most classes will have, but the constructor and the destructor, those have to be there. And so the constructor is code that runs automatically when you define a variable of type whatever your class is. So if I define a variable of type sensor, the constructor code, the constructor functional member of the class runs. So in our example from yesterday and from our programming assignment, that would be of type stack, okay? Well, that's one piece. When you define a variable, when it comes into existence, the constructor runs. When it ceases to exist, then a special functional member called the destructor runs. Now, the destructor, if this is a data structure like a stack, the destructor is going to have to deallocate any memory that's still allocated to the stack. Same thing with a queue, same thing linked list, binary trees, doesn't matter. Dynamically allocated memory has to be returned back to the environment, the runtime environment, okay? So these destructors for simple data structures or simple data storage classes usually don't have any code in them. But when they're for an abstract data type, for a stack or a queue or a linked list, then they have code in those destructors to deallocate memory. Now, basic class specification format has class, the keyword class, okay, right here, and then the class name, and then it has a block of code with a semicolon after it, and that block of code has particular keywords in it, public and private. Now, the default is private in a class, but if we really want the class to be usable, not everything can be private, otherwise nobody can use any of it, okay? And so we put things in public, such as the constructor and the destructor, because the runtime system, the program, has to be able to run those. And so those must be public. And then we also put in other methods for access and mutation and you know, working with the class, and those go in public. In private, we put the data. The data goes in private to keep it secure. There is a third level in C++, or a third type of access called protected, and we will avoid protected whenever it is possible. Protected is a hack in C++ to get around a couple of problems that Bjarne Stuvstrup, the inventor of C++, encountered when he was inventing the language. And so what happens with that protected is that basically anybody can just say, hey, I'm a friend of that class, I get access to all its protected data. And so that's particularly bad. We don't want to use protected unless we absolutely have to, okay? Now, that's the specification. If we were programming, we would also have an implementation that goes along with that. And so what I'm going to do now is I'm going to go through an extended chunk of programming. I'm not sure I'm going to get through all of that programming that I'm going to do for this class, for the class I'm creating in this particular lecture. But let's see how far I get and how much time it takes, okay? So I'm going to create a new class called sensor. This is similar to that sensor struct I had on the whiteboard a couple of days ago. And I know it's only a couple of days, but you know, this stuff is like doggy years, pandemic years. 2 days ago, I gave you, or I wrote on the whiteboard, the struct for a sensor, for a sensor network node, or a network sensor node. Today, I'm going to write a class for that. This is going to be the first class you've ever seen, unless you've been reading the book, which you should be doing. So this class is going to be for one of those sensor information stores. And so this is in place of what was previously a struct. And so, yeah, it was only 2 days ago, but it seems like about 10 days ago, really. I'm gonna think it's about 5 to 1 pandemic days to regular days. Okay, so I'm gonna drop the share of the PowerPoint at this point, and then I'm gonna share a Cygwin window so that you can see me program this. Okay, so I'm gonna share. So here we are. I'm just in a directory. In this directory, okay, I am going to edit the specification first. And so that's sensor.h. And sensor.h, I'm just going to start typing, even though I've already figured out exactly what I'm going to do in here. And I know what I want to include and all of that stuff. And in fact, I've already written all of this code once already today. So I'm going to include IOStream, okay? I'm going to use cout in some of these things, and so I'm going to include this. So what we've set up here now is the .h file is an include file to use the sensor class, but it's also including IOStream. I'm going to also do a using namespace standard so that I don't have to use the scoping operator for all of my cout and cin and that kind of stuff. Now, I'm going to put in a comment, and I'm going to say this is some preprocessor magic to keep the compiler from screaming at us. And so really what this is going to do is keep the compiler from creating a bunch of warnings about redefinitions. Just trust me on this. This is going to work, and this works just like an if statement. And I'm also going to, whoops, I'm going to change some of the config in my VI session here. So now, okay, I'm back ready to go. So this is, again, that #, which says this is a preprocessor directive. And I'm going to use something called if no def. So if sensor isn't defined in the preprocessor, then this if statement will execute. If it is defined, then it won't execute. Well, the first line of this is to define sensor, okay? So if this include file hasn't run yet in the compiling of our program, all of the include file will be included. If it has already been there, then the sensor is going to be defined, and it won't include all this stuff, so we won't get these redefinitions. Trust me on this. It's just something we do. If you think about it too hard, then it starts to hurt your brain. Okay, I'm going to define a constant int called max readings, just like I did 2 days ago, and that's going to be 5 for now. Okay, now I start off with that keyword class, and then I'm going to capitalize the word sensor. Convention is that classes and structs are initially capitalized, variables are not. So I initially capitalize sensor, okay? And now I need to open up my block, and then I'm going to put in the keyword public, okay? The keyword public : says the following things are given to the public user, the downstream programmer user of this class. They're allowed to be accessed. And so in here, I'm going to put in a constructor. Now the constructor is named the same as the class. It takes no parameters, and we don't even put on a return type for it. So this is particular to classes. The destructor has the same name, but it has a tilde in front of it. So it's tilde sensor, and no parameters, no return value. Okay, that is the constructor and the destructor. So I'm going to go up here, going to tab over, and I'm going to say constructor. And then I'm going to go down here and tab over and say destructor, just to remind me what those are. Okay. Now, remember we had an ID, a latitude, a longitude, and an array of readings. Each one of those things, because we're doing security now, we're walling off people from our private data, and all of those things are going to go in private. So for now, I'm going to stop writing the public parts, and I'm going to go down and put in our private data for this class. So I use the keyword private colon, and that says the rest of this stuff is private. And so I have an int ID, okay? And this is ID for the wireless network sensor, okay? I'm gonna have a double lat, and this is the latitude of the sensor's location. We have a double lon, which is the longitude of the sensor's, of the sensor's location, okay? And then I have double readings, which is an array with max readings number of entries, okay? And that's just gonna keep the last max readings number of readings. So if max readings is 5, like it is right now, this array will store 5 readings. If it's 6, it'll store 6 readings. If it's 2, it'll store 2 readings, okay? And then I'm gonna close off the class and hit the semicolon, okay? And then I'm gonna put the end of the preprocessor, if and def statement. And that is indeed a preprocessor directive. It is pound and if, and that's it. Okay, now I'm going to go back up and do those accessors and mutators that are required in order for us to access and change the ID, the latitude, the longitude, and the readings. Okay, so void set ID. And so this is why they're called getters and setters. Mutators are setters. They change things. Accessors are getters. That is, they retrieve things. And so this is going to set data. And if it's going to set the ID, it really needs an integer parameter. And I'm going to call that thing new ID. Okay. Whoops. I need another one called set lat. And that's going to have to take a double because looking down below, right down here, our latitude is a double. So the parameter that goes into the set latitude mutator has to be a double. And I'm going to call that latitude all spelled out. Okay. And then I need one for longitude as well. So set lon, and that's going to take a double. And I'm going to call that longitude. Okay. And then I need a setter for readings. I'm not going to set all the readings at once. The readings are going to come in from this wireless sensor network node, probably one every, say, 15 minutes or one every hour. And so I need a way to store those, store the new reading. And so I'm just going to call this set new reading, okay? And those readings are of type double, so I'm going to need double. And I'm just going to call it new read. Okay, there we go. So set new reading, and it's going to have a new read that's going to come in. So those are our mutators. Those are our setters. And they allow us to set anything inside of this data storage for a sensor node. Okay. But I also need getters because if I put the data in, but I can't get it back out, then that's a problem. And so I'm going to write setters for each one of these as well, or getters, excuse me. And those getters are going to return those values for us. Okay. So if I'm going to have a getter for an ID, that has to be of type int. And I'm going to call that get ID. And it's not going to take any parameters because I don't have to tell it where the ID is. The ID is in the class. It's in there already. It's right down here. And so this function is going to grab that value and return it. And so each one of these getters really is going to just be a return statement. That's essentially what these are. And so if I need a get latitude, that's going to be of type double for the return value, and get lat and no parameter. Double, get lon, no parameter. A double, get, and this one's going to be a little bit different because get reading, I have to know which reading I want to get. I have up to max readings, number of readings here. So I'm going to have a parameter on get reading, and it's going to be an integer, and it's going to be the index into the array. But I don't know how that stuff is stored. I don't know anything about arrays when I'm a user of this class. So I'm just going to send in a number, okay? And that's the number or the index to be read, okay? And then one last public function, void print censor with no parameters. This is going to print out everything in, just like in the example programs I did on Monday. This is going to print out all the data inside of one of these sensor nodes. Okay? That is the entirety of our specification for these sensor nodes, for these wireless sensor network nodes. Okay? Now, I'm just looking at what's going on in my meeting, and I'm trying to see how much time I've spent, and I really don't have a good way of doing that. So anyway, I've got the specification written. I'm going to get out of here. I'm saving that, and now I'm going to edit the implementation. Okay, and that's going to be called sensor.cpp. And this is going to have all of the implementation that's required for my sensor network. Now, this has a little bit different flavor to it because this is actually code. So the first thing I'm going to do in here is I'm going to include sensor.h. Okay. And I probably should have included, I'm going to put in a blank line here. I probably should have included IOStream as well, because I have to have a couple of error messages printed out in the setters and in the one getter. So we'll see those in a second. Okay. So I include IOStream, I include sensor.h, I do a using name space standard, and then I'm just going to define all of those member functions. That's what goes in the implementation, are the functional members. Doesn't matter if the functional member is public, private, or protected. God hope it isn't protected. But if it's public or private, the functional member definition and code goes in here. So the first one we're going to write is our constructor. And so in this case, we actually do have to use the scoping operator. It's the first time we've been required to use the scoping operator. And so this scoping operator says, in the namespace for the class sensor, I am going to define sensor. It will take no parameters. Let me get rid of this automatic indentation because it indents not according to my style. Okay. So this constructor gets run every time we define a variable of type sensor. But there's some things I want to do inside of the constructor because I don't want random garbage in all of those fields, all of those, the data for the sensor. So I'm going to zero all this stuff out. And this is really common with constructors, is that they zero out the private data. And so I'm going to need a local variable called I, because I'm going to have to run through all the readings and zero those out. And then I'm just going to set things to 0. ID equals 0. Lat equals 0. Lon equals 0. Now, I'm going to stop right here and talk about what's going on here for a second. This is a functional member that runs inside the class. When it's inside the class, it can directly access those private data members. And so you don't have to use a scoping operator. You don't have to tell it where ID is. This is my ID. So in every single object that is of type sensor ID, this code, these functional members will be able to access that object's ID, latitude, longitude readings. Okay. So next thing up, for I equals 0, I less than max readings, I plus plus. Okay, readings sub I equals 0. Okay. And then we just return. That's my constructor. I'm going to define in similar fashion. So in the scope of the class sensor, I'm going to define tilde sensor, which is the destructor. I don't have any dynamically allocated data here. I don't have anything to do, so I'm just going to zero it out, or just it's blank. There's no code in the destructor. Now, I might want to zero out those data members if there was sensitive data that I didn't want somebody to see, because this memory is going back to free memory, and I can't control that. I don't have access control inside my program of free memory. And so I might consider zeroing everything out in here, but in this case, I'm just not gonna. There's no dynamically allocated memory, and so therefore there's not much that I need to do. Now, I'm gonna write my first setter. So if you remember, my first setter was set ID. So I need to give it a type. That's the return type, void. And then I need to say, in the scope of the class sensor, get ID, or no, set ID. Sorry, I was doing the setter, not the getter. Set ID, int new ID. Okay. And here is the first time we get to see that security. My wireless sensor network nodes are never going to have a negative ID. And so I'm going to check that right here with an if statement. If new ID is greater than or equal to 0, because 0 could be a valid ID number. If it is greater than or equal to 0, then my ID, which is the ID inside the class, in the class's data storage, its private data member, is equal to new ID, which was the parameter into the function. Okay, that's all I needed to do. Pretty simple. But I also need to complain at the user if they gave me a negative number. And so I'm just going to do cout, and I'm going to scream at them a little bit with big capital letters, error, sensor ID must be a positive whole number. \n for new line, and that's it. So there we go. I'm going to close off my else, and then I'm going to do a return and close off the function. That is that. So at this point, I'm going to stop my lecture. If I've hit 50 minutes of lecture, which I can't tell you if I have or not, but I think I have, then we will continue on with the rest of the getters and setters on tomorrow's lecture. If not, if I still have some time, then I will produce a part 2 of this lecture, and I will continue on with defining a few more of these functional members for our class sensor. So with that, I'm going to exit that, and I'll bring down the Zoom recording, and we'll be done.